Yes, the distance and numerous turns in the grounding electrode conductor could be a significant concern during a lightning event. Lightning currents are extremely high and can induce substantial voltage drops within the grounding system. The longer the distance and the more turns present in the grounding electrode conductor, the greater the voltage drop experienced. This increased voltage drop could compromise the grounding system's ability to efficiently dissipate the lightning current, potentially leading to damage to the building and posing a risk to its occupants. Therefore, it's crucial to implement a grounding electrode conductor that is as short and straight as feasible. If turns are unavoidable in the grounding electrode conductor's path, they should be executed as gradually as possible. Additionally, the grounding electrode conductor must be appropriately sized in accordance with the requirements outlined in the National Electrical Code, commonly referred to as the NEC. Sizing is critical. Always consult the most recent edition of the NEC for specific requirements based on your installation. Several factors contribute to the effectiveness of a grounding system, and minimizing impedance is one of the most important. Firstly, the length of the grounding electrode conductor affects impedance. Shorter conductors have less impedance. Secondly, sharp bends increase impedance. Gradual bends are better than sharp turns. Thirdly, conductor material and size affects impedance. Copper generally offers lower impedance than aluminum for the same size. Larger conductors have lower impedance. Fourthly, the connection quality is key to low impedance. Use approved connectors and ensure they are properly installed. Fifthly, the soil resistivity impacts grounding effectiveness. Lower soil resistivity provides a better ground path. Sixthly, multiple grounding electrodes can lower overall impedance. Spacing them adequately is essential. Seventhly, the type of grounding electrode used also affects impedance. Rods, plates, and concrete encased electrodes each have different characteristics. Eighthly, the frequency of the current influences impedance. Lightning strikes involve high-frequency currents. Ninthly, proper bonding of metallic components minimizes potential differences. This is crucial for safety. Tenthly, surge protective devices, or SPDs, help to divert surge currents. They should be part of a comprehensive protection strategy. In addition to the grounding electrode conductor itself, it is equally important to ensure a robust and reliable connection between the grounding electrode and the earth. This connection should be established using a grounding clamp or another method approved by relevant standards and codes. Remember to consult the authority having jurisdiction, or AHJ. The AHJ can vary based on location and may have additional requirements beyond the NEC. Proper grounding is not only about safety, it's also about protecting sensitive electronic equipment from damage due to surges or electrical noise. In addition, lightning protection systems are designed to protect structures from damage due to lightning strikes. A typical lightning protection system includes air terminals, conductors, and grounding electrodes. Air terminals, often called lightning rods, are installed on the roof of a building. They are designed to intercept lightning strikes. Conductors are used to connect the air terminals to the grounding electrodes. These conductors provide a path for the lightning current to flow to ground. Grounding electrodes are buried in the earth and provide a low resistance path for the lightning current to dissipate. The NEC provides detailed requirements for lightning protection systems. These requirements cover the materials, installation, and testing of lightning protection systems. Some key aspects of lightning protection design include: firstly, zone of protection, which refers to the area around a lightning rod where a structure is protected from direct lightning strikes. Secondly, the cone of protection is a simplified model that assumes a lightning rod protects a cone-shaped area. The height of the rod determines the radius of the protected area at ground level. Thirdly, the rolling sphere method is a more advanced technique used to determine the zone of protection. It simulates a sphere rolling over the structure to identify areas vulnerable to lightning strikes. Fourthly, equipotential bonding involves connecting all metallic components within a structure to create a common electrical potential. This minimizes voltage differences and reduces the risk of side flashes. Fifthly, surge protection devices or SPD protect electronic equipment from voltage spikes caused by lightning strikes or other electrical disturbances. They divert excess voltage to ground. Sixthly, grounding electrode systems provide a low resistance path for lightning current to dissipate into the earth. They are a critical component of a lightning protection system. Seventhly, air terminals, also known as lightning rods, are designed to intercept lightning strikes and provide a safe path to ground. Eighthly, down conductors carry lightning current from the air terminals to the grounding electrode system. They should be installed in a way that minimizes bends and sharp turns. Ninthly, the NEC Article 250 and NFPA 780 provide detailed requirements for lightning protection systems. These standards cover design, installation, and maintenance. Tenthly, regular inspection and maintenance are essential to ensure the effectiveness of a lightning protection system. This includes checking for corrosion, loose connections, and damage to components. By following these guidelines and adhering to relevant codes and standards, you can help ensure that the building is properly grounded and effectively protected from the potentially devastating effects of lightning strikes. Remember that lightning protection is a specialized field, and consulting with qualified professionals is highly recommended. Also consult with qualified electrical engineers, lightning protection specialists, and local inspectors to design and install a compliant system.